On our last video we left off, again this is 9-7, factoring special cases. On our last video we left off where I just introduced this new rule for the difference of two squares, but I didn't get to the part where I talk about how you spot the difference of two squares. Spotting the difference of two squares is fairly easy considering it will always be a binomial, meaning you'll just have two terms where both the terms are perfect squares. So x squared is obviously a perfect square. Also, 81 is a perfect square. 9 times 9 is 81. Same thing with this second example. 16x squared is a perfect square because 4 times 4 is 16, and obviously x squared is a perfect square. Also, 49 is a perfect square because it's the product of 7 times 7. So let's look at some other examples. We're factoring the difference of two squares for when a is equal to 1. So we're going to factor a squared minus 16. Well, immediately I see this is definitely a difference of two squares problem because it's two binomials where the first and last terms are both perfect squares. So if I'm to factor it, then you know I'm going to end up with two binomials, 1 plus, 1 minus, where I just take the square root of the first term and the square root of the last term. And there's your answer. You know, to check it, all you have to do is FOIL. A times a squared. A times negative 4, negative 4a. 4 times a plus 4a. 4 times negative 4, negative 16. Obviously, the negative 4a plus 4a cancels, so you end up with a squared minus 16, and that is what we started with, so we did it correctly. Let's try another one, or another couple. Factor each expression and check your answer. We just checked our answer in the last one. We can do that here as well. So again, I can see immediately these are both the difference of two squares because obviously it's the difference. There's that subtraction sign, and these are both squares. So it's the difference of two squares. So I'm going to have two binomials, 1 plus, 1 minus, doesn't matter the order. Take the square root of the first term, x, and the square root of the last term, 6. There's your answer. To check it, just simply FOIL, x times x, x squared, x times negative 6, negative 6x, 6 times x plus 6x, and 6 times negative 6, negative 36. These cancel. X squared minus 36. We do, in fact, get what we started with, so we know our answer is correct. The second one, B, again, it is a difference of two squares. It's subtraction, and these are both perfect squares. So we know it will factor to be these two binomials, 1 addition, 1 subtraction, square root of the first term, and the square root of the last term. And there's our answer, and we can check it by FOILing. M times m squared, m times negative 10, negative 10m. Well, my board's kind of messing up there. Let me fix that. M squared, m times negative 10, negative 10m, 10 times m plus 10m, 10 times negative 10, negative 100. Our middle terms cancel, and we end up with m squared minus 100. So we know we did, in fact, do it correctly. Moving on to example 4, the difference of two squares for a is not equal to 1, meaning the coefficient in front of your squared term is not 1, and in fact we see it's not 1, but it still works the same way. You can ask yourself, is this a difference of two squares? Well, it's obviously a difference. Is this a perfect square? Yes. 3 times 3 is 9. Is 225 a perfect square? Yes. 15 times 15 is 225. So it does fall under the difference of two squares rule, where we know it always factors out to be two binomials, 1 addition, 1 subtraction, where we take the square root of the first term, the square root of 9 is 3, the square root of b squared is b, 3b, and the square root of the last term, the square root of 225 is 15, and 15. Again, you can check this by FOILing. 3b times 3b, 9b squared. 3b times negative 15, negative 45b. 15 times 3b plus 45, 45b. And 15 times negative 15, negative 225. We see again our middle terms cancel. 9b squared minus 225. So we know we factored correctly. Let's try another one. Quick check 4. Again, we're factoring the expression. You can check to see, is it the difference of two squares? It's definitely a difference. This is, in fact, a perfect square, and so is 64, so we know it falls under that rule where we have two binomials, 1 addition, 1 subtraction. We take the square root of the first term. The square root of 25 is 5. The square root of x squared is x, and that's our first term in each binomial. and the square root of the last term, 64, which is 8 and 8, and you can check it again by FOILing. All right, let's try one last example from this example 4. Again, is this the difference of two squares? Well, yeah, it's the difference, and these are both perfect squares, so we know we can use our rule for the difference of two squares where we have one addition and one subtraction binomial. We take the square root of the first term, 2w, and the square root of the last term, 7 and 7. And there we have it factored. All right, we're on to our very last example, example 5, factoring out a common factor. So you learned in the last lesson in 9-6 that any time you have a GCF that you can pull out, you should always pull that out first before you start factoring it into your binomials. Well, it's especially important here because if we look at this, it is a difference, but is 5 a perfect square? No. Is 80 a perfect square? No. So if we don't factor out that common factor, we can't use our rule for the difference of two squares. So looking at 5x squared and 80, I know that my common factor here is going to be 5. So I'm going to pull out a 5 from 5x squared and from 80. So 5 times x squared, which gives me 5x squared, minus 5 times a negative 16 would give me negative 80. So again, I just pulled out a 5 times x squared, 5x squared, 5 times negative 16, negative 80. So these two are still equal to each other. But now I have created my difference of two squares. So now I can use my rule on this x squared minus 16. So I still have the 5, and now I can factor out into my two binomials where I take the square root of the first term, x plus an x minus, and the square root of my last term, 4 and 4. And there we have 5x squared minus 80 factored. You can check it by first FOILing out your binomials and then multiplying them by 5. So let's do that. So I have my 5 times x, x squared, x times negative 4, negative 4x, 4 times x plus 4x, 4 times negative 16, or negative 4 is negative 16. Combine like terms, so I have 5 times x squared minus 16. You see we end up with what we had there. And then finally, 5x squared minus 80. So we do, in fact, get what we started with, so we know that we did factor it correctly. Let's try another one of those. Looking at 8y squared minus 50, again we notice this is not the difference of two perfect squares. 8 is not a perfect square, and 50 is not a perfect square. So we're going to have to factor out something first to make it a difference of two squares. Well, let's see. What's the common factor that 8 and 50 both have? Well, 2. You can pull out a 2 from 8y squared, and it becomes 4y squared. 2 times 4y squared is 8y squared. And 2 times negative 25 would give us negative 50. Now you see by pulling out that common factor of 2, we have created the difference of two squares, and we can use our rules. So we have 2 times, one addition, one subtraction. The square root of 4y squared is 2y, and the square root of 25 is 5. So here's our answer, and you can check it by, again, FOILing it out. Let's look at B. Again, we see with B, this is not the difference of two squares because 3 is not a perfect square and 75 is not a perfect square. But we can make it the difference of two squares by pulling out that common factor of 3. So I'm going to pull out a 3. 3 times c squared is 3c squared. 3 times negative 25 is negative 75. Now we have created the difference of two squares, and we can factor it using our rule. So I have 3 times, then my two binomials, one addition, one subtraction. The square root of the first term squared, c, and c. And the square root of the last term, 5 and 5. And there's your answer. Let's try one last example from example 5. Again, you see this is not the difference of two squares. 28 and 7, neither one are perfect squares. So we again have to pull out a common factor. I notice that 28 and 7 both have a common factor of 7. So I'll pull out 7. 7 times 4k squared gives me 28k squared. And 7 times negative 1 gives me negative 7. Now I have the difference of two squares, so I can use my rule. 7 times 1 addition, 1 subtraction. The square root of my first term, 2k, and the square root of 1, which is 1, and there's my answer. If you need more help on these, you can see some more examples in the book, or you can always come see me.